we have talked about this different states of matter, solid, liquid, gas. We've talked about their properties and things like that. What we're going to do here is we're going to start to talk about some of the energy that's involved in heating things up and changing their phases and cooling them down. And we're going to start by doing it in what's called a qualitative manner. And we're going to do that using what are called heating and cooling curves. Now, I'll give a caveat. Heating and cooling curves can be very quantitative. They can be exact and numerical. We're not going to do that in this class. We're going to kind of just use it as a way to talk about what happens. So what is a heating and cooling curve? Well, it's a graph where on the y-axis we have temperature, and on the x-axis for a heating curve we have heat added, which means as we go this direction on the curve, we are adding heat, and we're going to see what happens as we add heat. What we're going to do is we're going to start way down here at a low temperature, and we're going to start with ice. Now, how low of a temperature can I get ice to? Most people think, well, ice freezes at 0 degrees Celsius, so the lowest temperature you can get ice is 0 degrees Celsius. But that's not actually true. Most things, all things actually, can get below their freezing point. This ball, for instance, plastic ball. Plastic will melt eventually, right? Now, what's the temperature of this ball? The temperature of this ball is about the temperature of the room, which, it's a little warm in here, so maybe 21, 22 degrees Celsius, 80 degrees Fahrenheit or something like that. So it's a warm ball. But if I wanted to melt this, I'd have to heat it up to maybe 100 degrees Celsius. No, not in boiling water. 150, 200. I don't know what temperature this melts at, but it's getting a pretty warm temperature, which means I'm well below the temperature at which this melts. So can I get ice well below the temperature at which it melts? Absolutely. And in fact, most freezers, just freezer in your kitchen, has a temperature of about 0 degrees Fahrenheit, so certainly well below the freezing point of water, which is 32 degrees Fahrenheit. So I'm going to start with ice, and I'm just going to make up a number here, at minus 20 degrees Celsius. So over here on our temperature, we have minus 20 degrees Celsius. And then what we're going to do is we're going to add heat to it. Now, most people say, well, what happens when you add heat to ice is it melts. But it won't melt until it gets to what temperature? It won't melt until it gets to 0 degrees. Just like if I add heat to the plastic in this ball, it doesn't melt right away, right? I can put up my hands, whoosh, nope, no melted ball, even though I just added heat to it. What did I do? I heated up the ball. And I'll keep heating up the ball, making it warmer and warmer until it reaches its melting point. And the same thing for ice. As I add heat, as I move right on the curve, I'm just going to be warming up my ice until I end up with ice at 0 degrees Celsius. Because no ice is going to melt below 0 degrees Celsius, and so I have to warm up the ice to 0 degrees Celsius before it starts to melt. Now, I now have ice at 0 degrees Celsius. I'm going to keep adding heat. Okay? So as now I've got ice at 0 degrees Celsius, what's going to happen as I add heat? Now the ice is going to melt. Now if I add a tiny bit of heat and I've got this giant pile of ice, is it all going to melt? And the answer is no. Right? If I've got this giant pile of ice and I put a little blow dryer here, blowing heat on it, this part's going to melt. Right? So I've now got liquid here. But I still have solid all everywhere else, right? So I'm adding heat, but now I've got some liquid and some solid. Okay, that's great. What does that mean about the temperature? Well, what's the highest temperature solid water can exist? You're going to say, well, it's 0 degrees Celsius. That's when water melts. What's the lowest temperature that liquid water can exist? Well, it's 0 degrees Celsius. And if both of them exist at the same time, if we've got liquid water and solid water at the same time, and one can be no more than 0 degrees Celsius, and one can be no less than 0 degrees Celsius, what does the temperature have to be? The temperature has to be 0 degrees Celsius. So I'm adding heat. I've got my little heat gun here. I'm melting the ice slowly to make liquid. But what's my temperature? It's 0 degrees Celsius. Because otherwise, I wouldn't have any ice if it was warmer than that. or I wouldn't have any liquid if it was colder than that. So as I add heat, the temperature is not changing. And what I get in my cooling curve, or my heating curve, is I get a flat. I get this level spot here that says I'm adding heat, I'm melting the ice, but it's not all melted yet, which means I can't be greater than 0 degrees Celsius. Until I get to the point over here where I finally melted, just the last second I added just the last bit of heat, I've melted all my ice, and now I have a liquid at 0 degrees Celsius for just a moment. But the interesting thing that happens here is that a phase change occurs at a constant temperature. While you are changing phases, temperature can't change because the solid phase can't be above that temperature, the liquid phase can't be below that temperature, and so they're stuck at that temperature where they meet as you're adding heat. So now I've got a liquid at 0 degrees Celsius, and I take liquid water and I keep adding heat. What's going to happen? Well, I'm just going to keep warming it up, aren't I? And so I'm going to keep warming it up until what happens? Until I get a liquid at 100 degrees Celsius. Because something else so special happens to water at 100 degrees Celsius is it boils. Now, as I start to boil that water, does it boil instantaneously? When you boil a pot of water and it starts bubbling and bubbling and bubbling and bubbling, does it just go like that and all turn into a gas at once? No, we're adding heat and adding heat and adding heat and adding heat. And we're evaporating and evaporating. We're making gas, but it takes a long time. Now, what's the temperature of the liquid water? Well, it can't be more than 100, because if it was more than 100, it would be a gas. What's the temperature of the gas that's coming out right off the top? Well, it can't be less than 100, because then it would be a liquid. And so what we have is we've got another spot here where the temperature is not changing. It's 100 degrees Celsius while we're boiling until that moment where we've boiled it all off and we have a gas at 100 degrees Celsius. Now, what can we do with that gas? We can do pretty much whatever we want. I'm just going to draw an arrow up there saying we can pretty much heat that gas up as much as we want. There is a limit because at some point you do become a plasma. We're not going to get up into the thousands of Kelvin. So 100 degrees Celsius, you heat that gas up and you just get a really, really warm gas. But what we have here is we have a heating curve. And the heating curve has some important parts. One, it has two flat areas. One is for melting. The second is for boiling, where temperature is not changing because a phase change is occurring. It's also got three angled areas, one for each phase, solid, liquid, and gas, assuming that our heating curve covered that entire thing. If our heating curve started at 20 degrees Celsius, where water is a liquid, we wouldn't have any of this spot down here because we didn't start down there. But in this case, we did, and so we've got these three different areas. One last thing we want to look at on this curve is what phases are present during these different areas. So if we go back down here and we look, when we had ice at 0 degrees Celsius and we had ice at minus 20, the only phase present in that entire area was a solid because we had ice and ice. Here, however, when we start melting that ice, we're making a liquid, but we said it doesn't happen instantaneously. So there's points at which we have solid present. Right, we still got ice, and we've got a liquid present. So here in those flat parts, there's always two phases, solid and a liquid. How about here? At 100 degrees Celsius, we've got ourselves from 0 to 100, we've got ourselves just the liquid, one phase. So you see all those angled parts are single phase, all the flat parts are two phases. So having said that, what phases are present in this flat part? Hopefully you came up with a liquid turning into a gas. So we have a liquid and a gas. And then lastly up here, we've got a gas, and we can heat the gas pretty much as high as we want. So this is what's called a heating curve. Now I've shown this heating curve for water, but we can literally show it for any substance. You can show it for any substance that undergoes temperature changes when you heat and phase changes, which is every substance in the world. So we could do it for alcohols, we could do it for acetone, we could do it for copper, any of those substances. And what we want to be able to do with these is identify different parts of it, identify what phases we have in different parts. And we're not going to do it in this class, but these things can actually get a lot more complicated. There's some things out there that have several solid phases. And so you can get these multiple flat areas as opposed to just 2 flat areas. But we're just going to stick with these fairly simple heating and cooling curves. But so far all we've talked about is a heating curve. What's a cooling curve? Well, a cooling curve is exactly the same thing as a heating curve, but instead of adding heat, we're going to take away heat. So we're going to start with something that's already got a lot of energy, and we're going to take away that energy. I'm not going to spend near as much time on cooling curves, but it would look something like this. As we remove the heat, if we start with a gas at 120 degrees Celsius, this is for water, we cool down the gas until we start making a liquid. We condense the liquid. Now we've got that flat part there where we're making the liquid. We cool down the liquid until we start making ice. Then we can cool down the ice as cold as we want. So very, very similar in form, those cooling curves, but we're going to primarily focus our interest on the heating curves. So here's a chance for you to try identifying some things in a heating curve. Looking at this heating curve, at what temperature does this compound melt? So just take a moment, think about that. Try it out. Alrighty, what's melting? Melting is going from a solid to a liquid. Solids occur at very low temperatures, so you can make a guess that down here is where we had our solid, which means over here is where we had our liquid. Up here is where we had our gas. And melting is that conversion from solid to liquid, which is right here, somewhere around 18, 17, 15 degrees Celsius. Okay, you might have been tempted to write minus 20 because it was close to that, but no, it was close to positive 20. Minus 20 would be all the way down here. All right, so that is that one. Just reading off these curves, understanding those different parts of it. Next one, in the heating curve to the right, what phase or phases are present at 70 degrees Celsius? So again, you want to pause the video, try it out. Okay, what'd you do? For 70 degrees Celsius, you should have gone right across here and found, oh, I'm right at this thing, this flat area called a break. I'm right at that break there. What phases are present in that break? Well, at low temperature is my solid, liquid, gas. So here I must have a liquid and a gas present, which is E. All right, that's our discussion of heating curves and cooling curves. Thank you.